Welcome everybody to Algebra 2, Section 7.4, Solving Logarithmic Equations and Exponential Equations. So we're going to have a few different types of problems today, a few different types of equations, and our first type is when we have problems where you have a logarithm equal to another logarithm. When we have this type of problem, we will condense each logarithm if necessary. Then we're going to use what we're going to call the one-to-one property, to where if logarithm base b of m equals logarithm base b of n, notice both the same bases, then it must be true that m equals n. Very similar to when we were solving exponential equations back in section 2. Then we're going to solve and check for extraneous solutions. What we're looking for with extraneous solutions is you cannot have the log of a negative. And so I will note that you cannot have log of a negative number. And if that's the case, that solution would be extraneous if it causes it to happen. So we would need to note that. So on number 1, these logarithms are already condensed. There's nothing to condense about them. They're not separated into multiple logs or anything. And they're both base 5, meaning we can just set the insides equal to each other. So 5x plus 9 equals 6x. And so we start solving, so I'll subtract 5x from each side and get 9 equals x. And now I say, okay, I have to verify, would it make this first one negative or the second one negative? And if it makes either negative, let alone both, then it would be extraneous, and thus we'd have no solution because our only solution would be extraneous. But as long as it makes neither of them negative, 0 or positive is fine, then we are okay. And it makes neither negative, so x equals 9 is our answer. Same thing on 2 here. We have log base 2 on both sides, and so we take the insides and set them equal to each other. 1 minus 4n is equal to 2n plus 43. And so I'm going to add 4n to both sides and get 1 equals 6n plus 43. Then I will subtract 43 on both sides, giving me negative 42 equals 6n. Oh, not 62, but 6n. Then I'll divide both sides by 6. N equals negative 7. And if I plug in n equals negative 7, even though the value is negative, it makes neither of the logarithms negative, and that would be the potential issue. So negative 7 is the answer. On number 3, once again, we have the logs of the same base, both base 9, so we set the insides equal to each other. 6 minus 3w equals negative 2w. And so then we add 3w to both sides, giving us 6 equals w. And now if we plug in 6 to each of these, it actually makes both of them negative. We end up on the left one getting 6 minus 18, aka negative 12. On the right, we get negative 12. And so while they do equal each other, they're both negative, and thus extraneous solution here, and it's then no solution since our only solution is extraneous. Moving on to number 4 here. Number 4, we actually have to do that first step of condensing here because we have multiple logarithms here with the common log base of 10. So we condense them, and because they're adding, that means the insides will multiply. So we'll distribute the 4 to both the y and the 5, giving us log of 4y plus 20. And we have to write it in parentheses so that way we know that's all in the logarithm. And then now, since we have a log equal to a log with the same base, then we can set the insides equal to each other. 4y plus 20 equals 72. And I'll subtract 20 from both sides, giving me 4y. If it lets me click it. There we go. 4y equals 52. Divide both sides by 4. And y equals 13. And 13 makes this logarithm non-negative, and it can't change those logarithms since there's no variables. On to number 5, we also have to condense this one on the left here because this 3 is outside, so we'll make that 3 an exponent. And so this is log base 7 of 4 cubed equals log base 7 of 4a minus 8. And so we actually do 4 cubed and get log base 7 of 64 equals log base 7 of 4a minus 8. And then we set the insides of each log equal to each other because they have the same base. 64 equals 4a minus 8. And we end up getting here now as we subtract, or excuse me, add 8 to both sides. 72 equals 4a. Dividing by 4. And a equals 18, which causes no issues when we plug it back in and makes it a non-negative just fine. On number 6, we have to condense on left again. Since these are subtracting, we really divide the 68 by 4, giving us log base 4 of 17 equals log base 4 of 3n plus 11. And so we can set those equal to each other, since now they're both log base 4 on each side. 17 equals 3n plus 11. So I'm going to subtract 11 on both sides, giving me 6 equals 3n. Then I will divide 3 on both sides and get n equals 2, which works just fine when plugging it back in. Number 7 here, once again I have to make this an exponent, so I get log base 6 of 25 to the power of 1/2 equals log base 6 of 23 minus 4w. The power of 1/2 is the same thing as square rooting, and so thus the square root of 25 is 5, so log base 6 of 5 equals log base 6 of the quantity of 23 minus 4w. And so I set those insides equal to each other and I get 5 equals 23 minus 4w. Subtract 23 on both sides, giving me negative 18 equals negative 4w. Divide both sides by negative 4, and I'll get a fraction here, which is fine. And so w equals 9 over 2, or 4.5, 4.5, which doesn't make any of the logarithms negative, so it causes no issues. Number 8, I will need to condense these logarithms. So on the left, it just stays log base 3 of 2p minus 5. On the right, we make this to an exponent. And so we have log base 3 of 6 squared, and divided by, since we're subtracting, 4. And so I'll actually square the 6, give me log base 3 of the quantity of 2p minus 5 equals log base 3 of 36 over 4. And then I'll have log base 3 of the quantity of 2p minus 5, just staying the same again, equals log base 3 of 9. And now I can set these logarithms equal to each other, since it's fully condensed on the right-hand side, giving me 2p minus 5 equals 9. And if I add 5 to both sides, I get 2p equals 14. And then if I divide both sides by 2, I get p equals 7, which doesn't make any of the logarithms negative, so it's perfectly fine as an answer. 2 more examples of this type. No condensing to do here, so we can just set the insides equal to each other. So we get m squared equals 18 minus 7m. Anytime you have an exponent of 2, we want to set it equal to 0 and then solve. So I'm going to add 7m and subtract 18. I always want to move things toward my square because I want my square to be positive with the leading coefficient as a leading coefficient. So I want it to be a positive m squared, not a negative m squared. So I get m squared, if it lets me finish drawing that, there we go, plus 7m minus 18 equals 0. And with a quadratic, I always want to check to see if I can factor first. Then if I can't, then I'll look for other methods such as the quadratic formula. or completing the square, but since I can factor here, I will. And so the top is negative 18, the bottom is 7, since there's 3 terms. And a negative and a positive do the trick, and it's negative 2 and positive 9. Since it's a 1m squared, I can do the shortcut, giving me m minus 2 and m plus 9 equals 0. And so I get m minus 2 equals 0, and m plus 9 equals 0. I forgot to actually put the first one equal to 0. I should fix that. And I don't need parentheses. And so I solve the first one and get 2. I solve the second one and get negative 9. And now I have to check each of these to verify that neither of them will cause any negatives. So that way I see if either one's extraneous or perhaps both. And actually, as I check both of them, neither are extraneous. And so both are perfectly fine answers. Number 10, we do have to condense on the left here. And since these are adding two separate logarithms, we'll multiply the insides, giving us log base 10, since you don't see a base, of 2k squared equals log of the quantity of k squared plus 16. And I'll set the insides equal to each other, so 2k squared equals k squared plus 16. So I'm going to subtract k squared and 16, giving me k squared minus 16 equals 0. And actually here, I could factor, or I could even just solve by square rooting since I don't have a bx term. And I really like solving by square rooting, so I'm actually going to move that 16 back and just get k squared equals 16, and then square root both sides. Give me k equals both positive and negative 4. I have to check both positive 4 and negative 4 to verify they won't give me any extraneous solutions, and neither of them do, because when I square a negative in each of those original parentheses for the logarithms, they give me a positive number. Moving on to our second type of logarithm. This will be where you have the logarithm equal to a number rather than another logarithm. And so the first step is still similar where you condense the logarithm. You also just need to make sure you isolate the logarithm. Sometimes it won't be fully isolated. We'll see that on example 12, for instance, but not many others, if any others actually. Then on step 2, we'll write the equation in exponential form. So we'll do the spiral where we convert it from a logarithm to an exponential form. And then we'll solve and then check for extraneous solutions. Once again, just making sure that we don't have the logarithm of a negative with our solution. So on 11, there is one logarithm and there's nothing to get away from the logarithm. There's no like exterior things with the logarithm on the same side of the equal sign. So I'm going to go in spiral. And so what happens is my base stays as my base, so 2. And then this, what it was equal to, becomes my exponent of 6. And then what I was taking the logarithm of becomes what it's equal to, x minus 4. And now I can actually solve this equation. And so I do 2 to the power of 6, and 2 to the power of 6 is 64. And that equals x minus 4. And so now after I add 4, I'll get my answer. And that's going to be 68 equals x. And if I plug that back in, I get the logarithm of a positive 64. And since it's non-negative, that's my answer. So on to number 12 here, we do actually have to isolate the logarithm here because of this minus 7 is just hanging out there outside the logarithm. That's why this parentheses here is necessary. So that way we knew that the 8 was part of the logarithm, but the 7 is not. So after I add 7 to both sides, our logarithm will be isolated. So log base 3 of the quantity of 4x plus 8 equals 4. And so now, as we go to spiral, we'll have 3 to the power of 4 equals 4x plus 8. Remember, logarithms always equal to the exponent. And the base always stays the base. And 3 to the 4th is 81, and that'll equal 4x plus 8. And so if I subtract 8 on both sides, I get 73 equals 4x. And if I divide both sides by 4, that doesn't reduce or anything, so I can just say it's 73 over 4, or you can make it a decimal if you wanted. So 73 over 4 equals x, which doesn't make it a negative, so it's perfectly fine as an answer. On 13, since we have multiple logs, we have to condense them, just like we did in the previous type. And so as we have these adding, that means the insides multiply. And so 2x will distribute to both the x and the minus 5, giving us 2x squared minus 10x equals 2. And so now we spiral. We don't see a base for our logarithm, meaning our base is 10. So 10 to the power of 2 equals 2x squared minus 10x. So I actually do square the 10 and get 100 equals 2x squared minus 10x. And since I have a squared term, I will need to set this equal to 0 and solve. I always move things toward my x squared term because I want my x squared to be a positive as its leading coefficient. And so I'm going to have 2x squared minus 10x squared minus 100 as I subtract 100 for both sides. And rather than writing the equal 0 on the left, I just prefer it to be on the right. So I'm going to put it on the right and flip the equation around. And now I look to solve. Once again, I can use the same methods as I was talking about previously. So I can't use square rooting here since there is a bx term, but I do want to look for a GCF, and there is one. It is 2. And so that gives me x squared minus 5x minus 50. And that makes all my numbers smaller, as well as enables me to do the shortcut by factoring if I'm able to factor, which I'm going to check out right now. So I'd have negative 50 at the top and negative 5 at the bottom. And that would be negative 10, positive 5. And so I have 2 outside the parentheses, then x minus 10, and x plus 5. And that equals 0. And so now I set each of these equal to 0. And as I set each equal to 0, 2 cannot equal 0, so we can rule that out. X minus 10 equals 0, and x plus 5 equals 0. So the first one gives us x equals 10, and the second one gives us x equals negative 5. If I look at negative 5 further and try to plug this one in, I notice that it actually doesn't work. It makes both of the logarithms, are eventually condensed logarithm, negative, and that would be, or actually it doesn't make this condensed logarithm negative, but it makes this logarithm negative, or either of those original two, and that's an issue. And so because of that, it's extraneous. And so our only answer is x equals 10. On the number 14, I will need to condense these logarithms. So this is log of x squared. This 2 is really the exponent. And then divided by, since we're subtracting, 4 equals 2. I can't simplify this any further, so I'm going to go ahead and spiral. And so I have 10, the hidden base, to the power of 2 equals x squared over 4. 10 squared is 100 equals x squared over 4. So I have to get rid of the 4 in order to get x squared by itself. And so I'm going to multiply both sides by 4. And so I'm going to have 400 equals x squared. And normally when we have square terms, we want to solve for 0. But here, I could do that and then factor. Or, because I don't have a bx term, I can just look to square root right now, which is what I'm going to do. But otherwise, I could subtract 400 and then look to factor and to get x minus 20 and x plus 20. But as I square root, I get positive negative 20, which would lead me to the same results, equals x. As I verify to try to check both solutions, I notice that negative 20 is actually extraneous. Because as I plug it back into this logarithm right here, it doesn't work. It makes it a negative. And so x equals 20 is our only solution. Moving on to number 15. Once again, we need to condense this, and so I'll need to distribute this x, since this logarithms are adding. And so I'll have log base 6 of x squared plus 9x equals 2. That's fully condensed, so I'm going to go ahead and spiral. 6 to the power of 2 equals x squared plus 9x. I will go ahead and do 6 squared and get 36 equals x squared plus 9x. I have a squared term, an x squared, and I do have a bx, so I can't solve by square rooting. So I'm going to want to go ahead and set everything equal to 0. And so I'm going to move everything toward my squared term. And so I'm going to subtract 36 from both sides and then flip my equation around so I have my equal 0 on my right side, because I just prefer that. X squared plus 9x minus 36 equals 0. I always want to check to factor. There's no GCF. So as I check here, negative 36 on top, positive 9 on the bottom. And I look and I say, okay, does anything work by chance? And I'm like, really hoping it does. And I say, oh, you know what? Negative 3, positive 12, that does the trick. And so I get x minus 3 and x plus 12. Since I did have a 1x squared, I could use the shortcut here. And so now as I set each of those equal to 0, I get x minus 3 equals 0, x plus 12 equals 0, and then I'm going to solve these by adding 3 and subtracting 12. And the negative 12 ends up being an extraneous solution because it causes this one and this one to both be negative, even though it doesn't cause the condensed version to be negative. So it is extraneous. And x equals 3 is our only solution. On to 16 here. Two separate logarithms needing condensed again, so I will distribute this x inside the other one, and I will get log of the invisible base 10 of x squared minus 3x equals 1. So I look to spiral. 10 to the power of 1 equals x squared minus 3x. 10 to the power of 1 is just 10, so I subtract 10 from both sides, set it equal to 0 since I have a square term, and I do have a bx term, so I can't solve by square rooting. So I get x squared minus 3x minus 10 equals 0. I always try to factor. Negative 10 at the top, negative 3 at the bottom. And I end up getting negative 5, if it wanted to write a 5, positive 2. And so x minus 5, x plus 2 equals 0. And so I get x minus 5 equals 0. And x plus 2 equals 0. And so I get x equals 5, and x equals negative 2. And again, one of these ends up being extraneous. Now, it is possible you actually get two genuine solutions here. It just hasn't happened on these problems. But negative 2 ends up being extraneous because as you plug into either of these, you get negatives. And here it gives you a positive, but because it gives you a negative in at least one place, it's extraneous. And so x equals 5 is our only answer because it doesn't give us an extraneous solution anywhere. Moving on. So this is some review from 7.2 when we solved exponential equations. When we solved exponential equations, we noticed that we had to try and get a common base if we didn't have a common base already. So here we had 5 to the power and 25. And so our common base would be 5 because we always wanted to make bigger numbers into smaller numbers and then fractions into non-fractions was our goal. And so 5 to the power of n plus 10 can just remain unchanged, but 25 is really 5 squared. And so now since both sides are 5 raised to a power, we can set the powers equal to each other since they're the same power, the same base. N plus 10 equals 2. Subtract 10 and n equals negative 8, and that's our answer. On number 2, we need to change both bases because 9 is not a root of 3. Or say 9 is not a root of 27. 9 to no power is 27, or no integer power. And so 9 is really 3 squared, raised to the power of a plus 2. And then 27 is really 3 cubed, raised to the power of 4a minus 2. and then we multiply the 2 to each exponent and getting us 3 to the power of 2a plus 4. And you multiply the 3 to each exponent on this other one, giving us 3 to the power of 12a minus 6. Now, since we have common bases of 3, we set the exponents equal to each other. So we have 2a plus 4 equals 12a minus 6. So if I subtract 2a from both sides, I get 4 equals 10a minus 6. Then I will add 6 to both sides, giving me 10 equals 10a. And then dividing both sides by 10, a equals 1. Now we're going to encounter a new scenario to where what if a common base just isn't possible? So for example here, 2x equals 61. 61 is not a power of 2. There's no 2 to a certain power of 61. That just is not a thing. And we can't change both 2 and 61 to anything to get common bases. And so we have one of two methods to do. Now, of these methods, quite honestly, I'm not sure why anyone would ever choose to do method 1, but it is technically an available method, and so I will discuss it. But I will only be using method 2 for all of the problems for this type. And so you take the log of both sides and solve. And so what happens here is we say these are both going to be log base 10 of 2 to the power of x and log base 10 of 61. Which I don't need the parentheses, but I put them there. And so now what I can do here is I can move this x to be a coefficient. Get x times the log of 2 equals the log of 61. And now to get x by itself, I would have to divide to undo the multiplication. So I divide by log of 2, just like it's any number. Just like I divide by both sides by 2 or by 4 or by 8. I'm just dividing by the log of 2. And anything divided by itself other than 0 is 1. So I get x equals whatever log 61 divided by log 2 is. And so we just type that into our calculator with base 10. So we just use the log button, log 61 divided by log 2, round to 2 decimals, and we get approximately 5.93. Now you'll notice as we do method 2 that it shortcuts a lot of that out. It makes the problem a lot less messy. And what you do is you essentially just spiral the problem and turn it into a logarithm, one single logarithm. And so the base is still the base, so it's log base 2 of 61 equals x. And then you use your change of base formula, which is exactly what we did back in section 3 when we learned the change of base formula. And so we do log of 61 with base 10 now over log of 2 with base 10 equals x. And then we actually just use our calculator for that again. And just like we did a moment ago, we get 5.93 approximately to 2 decimal places. And like I said, I always choose method 2 rather than choosing method 1 because it achieves the same results and to me is a lot less convoluted. But if you prefer method 1, please do method 1. So now I'll be solving problems using this method. And it says round to the nearest 10,000ths, but I'm changing that to round to the nearest 100th because I want to do 2 decimals rather than 4 decimals. So 12 to the power of x equals 8. And essentially when you would do this is when your, like I said, when your exponent is a variable and when you don't have the ability to get common bases, which I will go and spoil is the case on this whole chunk of problems that we're about to do. So as we have 12 to the power of x equals 8, we will go ahead and spiral and get log base 12 of 8 equals x. Use the change of base formula and get log of 8 equal over log of 12 equals x. And our calculator can tell us that x is approximately 0.84. 4 to the nearest hundredth, or 2 decimal places. On to number 4. Once again, spiral to turn it into a logarithm. Log base 8 of 92 equals m minus 7. Then we'll do the change of base again. Log of 92 over log of 8 equals m minus 7. Our calculator tells us that this is approximately 2.18 equals m minus 7. But we're not done here because we actually have to add 7 to get m by itself. And so if we add 7, we end up getting m to be approximately 9.18. So the exact same thing as the last problem, but different numbers for our logarithms, and then we just added 7 at the end. On number 5, we do have another step. Oop, my iPad decided to close the app. So let's give it a second as it reopens. There we go. As we move on to number 5 here, we have 4 times 7n equals 148. So whatever's being raised to a power is not isolated, so we need to make it isolated by undoing whatever's around it. So in this case, that's multiplication. So we undo that by dividing by 4 on both sides. We cannot multiply 4 and 7 together because that is going outside the order of operations. That would be multiplying before doing an exponent, and that is against the order of operations. So we have to undo things instead. And so those 4's undo each other, giving us 7 to the power of n equals 37, which is quite convenient because that makes our number smaller, and I prefer smaller numbers. So now I go ahead and spiral here, giving me log base 7 of 37 equals n. So I'll do my change of base and get log of 37 over log of 7 equals n, and I'll let my calculator do the heavy lifting here, telling me that n is approximately 1.86. Number 6 here. Once again, what's being raised to a power is not by itself, so I need to undo the minus 5 by adding 5. So 4 to the power of 3w is equal to 8. And so then we'll spiral and get log base 8 it's not even log base 8, log base 4, our base stays the base, so silly Mr. Kossel, of 8 equals 3w. And we use our change of base to get log of 8 over log of 4 equals 3w. Our calculator will tell us that this is 1.5. And then we have to divide both sides by 3. And so w ends up being 0.5 or just 0.5 or 1/2. And that's our answer. Now I should note we do actually still have to check for extraneous solutions on some of these problems. And by some of these problems, I mean we still have the same issue as far as we can't have the logarithm of a negative. So if our logarithm were to ever contain a variable, which none of these have, then we'd have to ensure that we could plug it back in to make sure it wouldn't contain a negative number. But once again, none of these have that issue that we've seen. But doesn't mean it won't happen. Number 7. I should clarify, we won't see that here though, where we have a variable inside the logarithm on these types of problems. Anyway, so we isolate this, and so we need to get rid of the 7 and the minus. They're actually going to be two separate things. So we subtract the 7 first and get negative 4 to the power of x plus 1 equals 11. Then we divide or multiply both sides by negative 1, depending on your preference and how you think about it. And we get 4 to the power of x plus 1 equals negative 11. We do our spiral, and I get log base 4 of negative 11 equals x plus 11. And I could try to continue solving here, but I'll notice if I use my calculator at a later step after I use change of base, that'll give me an error. Because you can't have the logarithm of a negative. That's an issue right here that we should be noticing. And once we notice that, we say, oh, there's going to be no solution to this problem. This problem cannot be solved because you cannot have a logarithm of a negative. Number 8. In order to get what it's being raised to a power by itself, we have to undo the multiplication of 10 by dividing by 10, giving us 5 to the power of 3k minus 3 equals 4. So now we spiral, giving me log base 5 of 4 rather equals 3k minus 3. And then I will use my change of base and get log base 4 over log of 5. I said log base 4, but log of 4 base 10. And log of 5 equals 3k minus 3. And my calculator will tell me that that ends up being approximately 0.86 equals 3k minus 3. And then we add 3 and divide by 3. So if I add 3, I get 3.86 equals 3k. And then if I divide both sides by 3, we end up getting approximately 1.29 equals k. On number 9, we have to get rid of the 15 and the 4. We'll do the 15 first, giving us 4 times, and 3 to the power of n rather, equals 344. And we'll divide both sides by 4, giving me 3 to the power of n equals 86. Then we will spiral and turn this into a logarithm, giving me log base 3 of 86 equals n. Now I'll use my change of base formula, giving me log of 86 over log of 3 equals n. And so n is approximately, rounded to 2 decimal places, 4.05. Moving on to number 10, we'll need to get rid of the negative 2 and the 7. I get rid of the addition and subtraction first, so the 7 has to go. So negative 2 times 5 to the power of p equals negative 70. I'll divide both sides by negative 2 because it's multiplying, giving me 5 to the power of p equals 35. Now that what it's being raised to a power is by itself, I will spiral and turn it into a logarithm, giving me log base 5 of 35 equals p. And so now I will use my change of base, giving me log of 35 over log of 5 equals p. Typing this into our calculator will tell us that p is approximately 2.21. Moving on to number 11. We need to get rid of the 5 and the 1 coming first. So 5 times 9 to the power of v minus 1 is equal to 180. Divide both sides by 5, and that gives us 9 to the power of v minus 1 equals 36. Then we'll spiral and turn it into a logarithm, giving us log base 9 of 36 equals v minus 1. We'll use our change of base, giving us log of 36 over log of 9 equals v minus 1. And that tells me that we get 1.63 is equal to v minus 1. Adding 1 to both sides to get approximately 2.63 to be v. On number 12, more isolation needs to occur before we can turn it into a logarithm. So I will add 3 first and get 8 times 11 to the power of 7k equals 216. Then I'll divide both sides by 8. And I get 11 to the power of 7k equals 27. Then I will turn this into a logarithm, give me log base 11 of 27 equals 7k. Then I will use my change of base, give me log of 27 over log of 11 equals 7k. And so then I get, from my calculator, 1.38 is equal to 7k, or approximately 7k. And dividing both sides by 7, k is approximately 0.20 as I round the nearest hundredth. Moving on to number 13 here, I will add 2 and then divide by 6. So 6 times 16 to the power of 7y plus 2 equals 84. Divide both sides by 6. And I get 16 to the power of 7y plus 2 equals 14. Then I will spiral both sides, giving me log base 16 of 14 equals 7y plus 2. Then I'll use my change of base and get log of 14 over log of 16 equals 7y plus 2. So my calculator will tell me that 7y plus 2 would be approximately 0.95. So then I'll subtract 2 and give me negative 1.05 equals 7y. And I'll divide both sides by 7, giving me negative 0.15 to be y. Number 14, last but not least, I will subtract 10 first, give me 3 times 8 to the power of 3 minus 7n equals 84. Then I'll divide both sides by 3, give me 8 to the power of 3 minus 7n equals 28. Then I will spiral and turn it into a logarithm, giving me log base 8 of 28 equals 3 minus 7n. So then I'll use change of base to give me log of 28 over log of 8 equals 3 minus 7n. When we divide those logarithms, we end up getting 1.60 equals 3 minus 7n. So I subtract 3 from both sides, and then that would give me negative 1.40 equals negative 7n. And I divide both sides by negative 7. And n is approximately equal to 0.2, or 0.2. That'd be 0.20 in case you're curious. And that would be our answer. And that wraps up section 4 of Algebra 2.